Let me introduce our next speaker, Austen Lamacraft from University of Cambridge. He's going to talk about quantum ground states from reinforcement learning. So Austen, please unmute yourself and share your screen.
Okay, right, Ben, can you hear me?
Yeah.
Okay, great. So thanks, Ben, and thanks to all the other participants for being here.
Yes.
Yeah, okay, good. So this is a project that I've been working on with two master's students, Ariel Barr and Willem Gispen. And the idea is to use reinforcement learning to tell us something about the ground states of quantum mechanical systems. And so to understand what the challenge that's presented to us by many-body quantum mechanics, let's look at the Schrödinger equation. So this basic eigenvalue equation involving a Hamiltonian partial differential operator, H. And it involves the potential energy, V, and an interaction, U, between pairs of particles. And if you wanted to solve this easy by a finite element, you're working on a grid of L to the 3n points in 3n dimensions. And so as the number of particles n increases, we are faced with an exponential explosion in the difficulty of the problem. So atoms and molecules rapidly become very hard. Dealing with matter, I'm a condensed matter physicist by training, is where you've got an Avogadro's number of particles becomes impossible. So what you do, in fact, is work with approximate wave functions. You introduce some kind of family of many-body wave functions, and then you use a variational principle to try and optimize the parameters of that family. You do that by evaluating the expectation of the Hamiltonian operator, and that expectation involves an integral over all of these n coordinates. So the challenge is here, evidently finding a flexible family of wave functions, evaluating this expectation, and then doing the optimization. And historically, what's been done is a kind of feature engineering, where you have a succession of more involved approximations to the many-body wave function. The first one is the Hartree-Fock approximation, where you just have a product wave function over the different particle coordinates. And then you can make that more complicated with something called a Jastrow factor, which takes into account pair correlations, which depend just upon interparticle separations. And this is just the first two stages of a whole hierarchy of complicated approximations that have been developed over the last century. And this is an input to evaluating this expectation value of the energy. But the way that's done is to interpret the modulus squared of the wave function as a probability distribution, and then evaluate the expectation using Monte Carlo sampling. And this is the foundation of the variational Monte Carlo technique. Now, and it's also the place where neural networks have been brought in the last few years. So the idea here is, instead of doing this feature engineering, we model the wave function, the many-body wave function, using a neural network, and then we optimize in the usual way. And the modern era for this kind of approach really starts with this paper of Calao and Troyer from 2017, which was applied to lattice models. And there's been very many papers since then, and maybe I'd just like to highlight 3 papers, all from 2019, which dealt with the many electron problem and all its complexities. So there are different representations of quantum mechanics, not just the Schrödinger equation. In particular, there's a path integral representation due to Richard Feynman. And what we're going to do in this work is we're going to work with that representation and learn the path integral instead of learning the wave function. Okay, so for the rest of the time, this is what I'll tell you about. First, we'll go over some theory of the path integral, and then the loss that we derive, the loss function that we get that lies behind our approach. I'll describe how we train to optimize that loss, and some features of the architectures we need for dealing with many identical particle systems. And then I'll go on to describe some initial experiments, so really proof of principle experiments, just to show that this approach is working before telling you about some future directions for this kind of approach. Okay, so the path integral is a tool for solving the imaginary time Schrödinger equation. So this is where you have time dependence, as illustrated here. And the solution is expressed as an expectation over Brownian paths, together with an initial condition for the wave function. And this expectation is called the Feynman-Katz formula. And as you can see, what appears there is an exponential weight, which involves the potential energy. And the consequence of this is that regions of repulsive potential, where V is positive, are going to be penalized by this exponential weight, and regions of attractive potential are going to be encouraged. So this re-weights the ensemble of trajectories. And the connection to the ground state is, if we let the time go to infinity, then the wave function tends towards the ground state wave function with an exponential factor, which knows about the ground state energy. So just as a parenthetical comment, this is the foundation of various numerical techniques, notably the path integral Monte Carlo technique. So here in this picture, you can see the Feynman trajectories of a system of interacting bosons. And the fact that these trajectories don't get close to each other is a consequence of the repulsive interactions between the particles. But we're going to be applying methods of deep learning, so we need a loss function we can optimize. And so we interpret the Feynman-Katz formula as giving us a path measure, a measure over the space of paths. And although it may not be immediately obvious, there's a result that tells us that that measure is Markovian. And so it can be written, the paths can be written as some stochastic differential equation in terms of some multidimensional Brownian motion B and some drift function, which we don't know. So what lies behind our approach is a model for that drift function. And once you've got a model for the drift, that defines another measure, P sub V. And our loss function is going to be the KL divergence between those two path measures. Okay. So which involves a logarithm of the Radon-Nikodym derivative. And so because this loss function, as we'll see shortly, is integrated over paths, it's integrated over some history, this looks like a reinforcement learning or optimal control problem where we have to choose the best control, the best drift to minimize this loss function. Okay, so just to put some more mathematical flesh on that, the log of this relative likelihood that appears in the KL divergence has this form. And the important part really is this curly L, which is a integral over the path. And it depends upon the drift function, which is the thing is going to be our model. And it also involves the potential function, big V. And when we deal with interacting particles, that will also involve the interactions between particles. And so what we're going to do is simulate a whole bunch of trajectories underneath under our stochastic differential equation. And then we're going to use those to get a Monte Carlo estimate for the KL divergence. Of course, we want to, at the end of the day, optimize, do automatic differentiation through this whole thing. So we want to be able to differentiate through the expectation. But because these trajectories are just obtained from some discretization of an SDE, they'll be written in terms of normal increments. So differentiating through the expectation there is just the same, really, as the reparameterization trick that's used, for example, in variational autoencoders or other probabilistic models. Now, because the KL divergence is positive and vanishes when the two path measures coincide, we can see that the expectation of this quantity, curly E, is going to be lower bounded by E naught times the time window we're integrating over. So that gives us access to the ground state energy. Okay, so just to summarize, the overall strategy is going to be to represent that drift in the stochastic differential equation by a neural network with some parameters. We'll take batches of SDE trajectories, we'll form this integrated cost L, and then we'll just optimize this by backpropagating through the solutions of these SDEs that we've got. Now, if we're dealing with identical particles, many identical particles, we've got an additional feature or additional structure we want to build into the system, and namely that's permutation equivariance. So in terms of the drift function, that means that if I permute the positions of the particles, then I'm going to permute the drift velocities assigned to each particle in exactly the same way. And in recent years, there have been a number of ways suggested of doing that. The one was called deep sets from a few years ago. The way that we found works best is based on single particle and pair features, and it looks like this. The idea is that we take our positions and our pairwise separations of the particles, and we use those to build some features H sub I in terms of some neural network sigma and little pi, and also some pairwise features H sub ij in terms of another network big pi. And then we can just repeat that process as stacking these things together. So then we have some features H tilde sub I written in terms of the H's, and likewise some H tilde sub ij written in terms of the Hij's. And then eventually we build, at the end of the day, a fully permutation equivariant drift function, which can be, however, very expressive if we stack layers together. Okay, so that's how we do it. And the initial experiments we did were some systems from atomic physics, so hydrogen helium atom and the hydrogen molecule, and also a problem from many body physics of two-dimensional bosons in a harmonic potential with Gaussian interactions. And so in terms of the network architecture, we were just using a single hidden layer to model our drift function with a width that went between 64 and 256 units, hard tangent activation. And we didn't make any additional use of symmetries in these atomic physics problems because that doesn't really generalize to more complicated systems. We were only dealing with the permutation invariance. And code's all available at this repo here. So just to give a quick example, this is the Hamiltonian for the 2-electron atom helium, where we don't know the wave function exactly, but we have a very good approximate value. And one additional thing that's important in these kinds of systems is to build in a cusp condition on the wave function, which is present because of the Coulomb interactions. We can do that by putting in a skip connection into our network, which models the drift. A hydrogen molecule is the same kind of system where the two protons are now separated. You've got an additional parameter there, which is the internuclear separation, which you can tune equilibrium separations at 1.4 atomic units. If you stretch the molecule, then in the probability distribution, you can see two clouds emerging. Okay, so this is just a summary of the results of our experiments on these atomic systems compared to Hartree Fock. So these are by no means state of the art at all, but they just show that we're in the right domain. We're beating Hartree Fock by a factor of 10. You know, but there's plenty of room for improvement to get to the state of the art for neural approaches or indeed other approaches. But this shows where basically everything is working well. And the other example we looked at was 2D Gaussian bosons with a harmonic potential and Gaussian interactions, which we took from this paper in 2017. This is how the learned drift looks for the orange boson in the presence of those green bosons. Just as an illustration, you can see that drift is trying to keep the orange boson away from the green bosons, which is what you would expect it to do in the presence of repulsive interactions. And here's the comparison with these exact results from the earlier paper, which were based on exact diagonalization. So you can see we're within 1%, even with strong interactions. So the outlook here, there are many ways to go. We can look at excited states with finite angular momentum. That's going to involve a drift function which is not reversible. Looking at fermions in a more serious way involves confronting the sign problem coming from the exclusion principle. The thing we're working on now, which we're excited about, is extending all this to the kind of models we have in condensed matter physics that live on the lattice. And so that's the kind of thing you see there on the right, particles moving only on discrete lattice sites. We can formulate all of this probabilistic approach in terms of these discrete models too. And of course, there's been a great deal of success in reinforcement learning applied to 2D lattice problems like gameplay. And we hope to use some of the to leverage our work on lattice problems. Okay, and I think that's all I wanted to say. Thank you.
Is it possible to extend this to cases with anti-symmetry? So Austen, you can.
Yeah, so it requires introducing a drift which corresponds to putting nodes into the wave function. So there have been some pre-neural network attempts to do that, and so that's what you would need to do to make this formalism work. So that would roughly be the equivalent of dealing with the fixed node approximation.
Here's a question for Austen. What is the initialization of the wave function in H2 example?
H2, okay, so that's a sum of two drifts which give rise to this Kato cusp condition that I mentioned. So that would, in terms of a wave function, correspond to a hydrogen wave function around each of the two protons. So one which doesn't take into account any correlations. So that's how we, that's just done with the skip connection, and everything else in the network is initialized to 0.
Can you comment on the pros and cons of your method compared to VMC plus neural network approaches?
Well, I guess it's all in the proof will be in the pudding in the long run. But the I guess one difference is that when you're learning a wave function, you have to somehow pool all the information at the end of the day from your configuration and then spit out a single number, which is the wave function. Whereas in this approach, you're modeling a drift, which is telling you how the particles want to move. So there's no, you don't, if you like, have to learn how to pull that information the correct way into a single number. The other issue is that there's no separate sampling step. So when you are doing VMC, you have to have a separate sampler to generate your samples in the wave function, whereas in this case the sampling is intrinsic to the algorithm. So, but you know, I guess the question is, you know, can one actually get the kind of numerical results that you see already in VMC, and that's something for the future.
Can you see a way forward with your approach to estimate energy gaps for trial ground state wave functions? I have quantum Hall states in mind.
So this is I guess energy gaps between ground and first excited states. Is that right? That would require a ansatz drift for the first excited state. So probably it's the short answer. I don't know, but I guess how good it is just depends on how good your ansatz for that first excited state drift. There's no so you'd have to rely on symmetry in some way. It would be special to the particular system, I think.